Good evening, everybody. It is day 7 of Advent of Code, and we have just a little under 6 minutes until tonight's puzzle unlocks. As always, we're going to be working on solving these puzzles in C++. If you have any questions that you want me to answer, or you just want to say hi, feel free to drop that in the chat. In the few minutes that we have before we start tonight's puzzle, before that unlocks, I just wanted to cover a couple of things. First of all, I said over the last couple of days while we were talking more about Day 4 solutions that the C++ library does not have regular expression support. I was wrong about that. I completely forgot that it did. It was introduced in C++ 11. Somebody named Paul Terra on Twitter pointed that out to me. So there is a regular expression library as part of the standard library in C++. I looked up the reference here. You can kind of see it here. I don't know. The API looks like it might be a little bit clunky. I don't really... I guess I would have to, try using it to really make an informed judgment about that. If I need to use regular expressions, I'm definitely going to continue using RE2 because I'm a lot more familiar with that. And, I know how it works and I know the performance is good. And I should also mention that the comment I got in Twitter about the regular expression library in the C++ standard library is that me saying that it doesn't exist was the quote-unquote correct way of viewing it. So maybe it's not that great. But it is there. Just wanted to clarify that. Another thing I wanted to talk about is just to say thank you to Eric Wastel, who has made all of these puzzles and who runs Advent of Code, who comes up with this on his own and then revises things with the help of a bunch of beta testers for his puzzles. This is a pretty amazing community and an amazing thing that we all get to do together to have fun every December. And it's pretty awesome that he puts that out there in the world. So I saw this really great article, this Advent of Code Builds a Programming Community Around Puzzles article. I will paste this link. I'm going to paste it in the chat right now. And I will also put the link down in the description if you're watching this on YouTube. But I think that it's a really cool article kind of talking about the history of it and talking about how Eric has set up all these puzzles for all of us to have fun with. And so I thought it was really cool to read about it, and I just wanted to say thanks, Eric, for giving us this really fun thing to do every year. So we have a little under 3 minutes until tonight's puzzle unlocks. So I haven't really revised anything on any previous day's puzzles since last night's stream. But one thing that we can do in the meantime, as we usually try and do before the puzzle actually drops, is to make just the bare bones scaffolding for our solution program. So we'll once again have this very minimal C++ program, and we'll make a build file for the Bazel build system to be able to build it. And we can go ahead and just run that, confirm everything works okay. And, it has no output, but everything compiled fine. We are ready to go. So we still have about a minute and a half until today's puzzle unlocks. Thank you to everyone joining the stream. Tell your friends, or, to people who are watching on YouTube, the replay on YouTube. Thank you for watching. As always, I'm glad to answer questions if anybody has them that they want to drop into chat. One thing that I did want to say in just the 1 minute that we have before tonight's puzzle unlocks is puzzles tend to get more difficult as time goes on, and of course everybody's idea of what constitutes a difficult puzzle is different. But I fully expect that sometime over the next couple of weeks I might get stumped on a couple of these puzzles, or I might go down some garden paths and decide that, some part of my solution was wrong. And, I hope you'll bear with me and, me trying to talk through my process. I might not get everything solved on the night of. But, that's part of what makes this fun. You get to stretch your mind a little bit and try and figure some stuff out. So I ask ahead of time that you bear with me for that, and we will continue to have fun trying to tackle these together. So, almost the moment of truth for tonight's puzzle. 2 seconds, 1 second, let's go! Land at the regional airport for your next flight. In fact, it looks like you'll even have time to grab some food. Oh, there's issues in luggage processing. Due to recent regulations, many rules are being enforced about bags and their contents. Bags must be color-coded and must contain specific quantities of other color-coded bags. Light red bags contain 1 bright white bag, 2 muted yellow bags. Oh boy. If you wanted to carry in it at least 1 other bag, how many different bag colors would you need to be valid for the outermost bag? In other words, how many colors can eventually contain at least 1 shiny gold bag? Okay. So let's save our puzzle input. So basically, let's actually look at what that input looks like. I'm sure there's going to be tons and tons of rules. Yep. So what this looks like is we want to find bags that contain, so for shiny gold, okay, so we find shiny gold, and we want to kind of backtrack and find all the different bag colors, outermost bag colors that can contain our shiny gold bag. So it seems like we kind of have a graph here where each node on the graph is a bag color, and then there are links between what bags can hold what other bags. And we want to backtrack along those links to everything that can hold a shiny gold bag, or everything that can transitively hold a shiny gold bag, until there are no more possible bags to visit. So the things that we need to do are we need to parse all of these rules, and we need to make a graph out of them. So we'll make a class called BagGraph, which will be the whole big thing. And so, like I said, the nodes in this graph are going to be the different colors of bags, and then the edges between the nodes are going to be the contains relationships. So in this case, though, we want to start with something that is contained, and then backtrack, and then be able to backtrack. And actually, we can kind of build the edges in both directions, just so we have, an easy way to look up each side. We can say, like have an is contained by and a contains relationship, and we can build those both at the same time. So, and I mean, really, we only need the is contained by to solve this first part of the problem. I get kind of an inkling we might need the relationship going the other way for the second part of the problem, but we'll see. So what I'm going to do here is have a flat hash map of strings to string, standard string to standard string, excuse me, that will be the contained by relationship. And right now, for the first part of this, I'm not really going to care about how many are contained by, just like that any gold bag can be contained by, because that's all we're being asked to for the first part. We may have to come back and revisit that for the second part. But I guess tonight I'm feeling like being kind of minimal for the first part solution. So we want to be able to add a rule to this graph. So each rule is a separate line here. Like, for example, dull bronze bags contain however many of each of these kind of bags. Yes. Okay. Okay. Some more fancy string processing here, but let's say add rule. We get this rule description. And to parse this, okay, so we're going to set to have some description of a color. Are the colors always described by 2 words, I wonder? Because if they are, that might make the parsing a little bit simpler. Let's see here. Yeah, the puzzle doesn't say anything about it, about color names always being 2 letters, so I kind of feel like this could be anything. Let's see. So I'm going to use abseil stir split and split this on commas. And actually the comma and space, because that's going to make it a little easier. Just because, well, So all these rules seem to end in a period. Sorry, I'm just thinking aloud to myself here. So first thing I'm going to do is just chop off that period at the end. Move suffix 1. And then the next thing I'm going to do is split apart the parts of the rule by the comma delimiters. So so when there are multiple clauses by this that have commas between them, we will split all of the stuff by commas. So we have the basic form of a rule here, and then we have additional stuff on the tail that we will process. And again, I could probably do some parts of this fancy with regular expressions. I'm going to be leaning on stir split a lot because that is the easiest way for me to think about it right now. Your mileage, of course, may vary. So we're going to split the rule, and we're going to split it by comma, then space. So we'll get, all of our additional clauses. The first rule part is going to be let's see. There's always going to be this bags contain substring. So let's go ahead and let's go ahead and split the first part by that. So we'll say I am not necessarily proud of any of the string parsing code that I'm writing here, but hopefully when we get to the actual graph processing part, I will feel a little bit better about myself. That should have two parts. There is the color part beforehand, and then part of the tail of the rule that's the same. So and then I am actually going to go back and replace the first part of this rule parts vector because we've parsed out the head container, because this part is the same as all the rest of the clauses that we parsed out in the rest. So I'm going to go ahead and reuse that first part of the vector. Okay. So now this container should be the name of the containing type of bag. And then all of these rule parts here will be strings like 3 faded red bags, 2 vibrant black bags, etc., etc. So now let's, you know what? This is getting a little complicated. Let's go ahead and write a helper function, and we'll say call it parsed bags. We'll have a color, and we'll have a count. So we'll write this helper function, and this can actually be static. It doesn't need to know anything about the contents of the class. So we want to So I want to trim off the bags part on just the bag or bags on the end, and then we can just split it apart into the number part at the beginning for the count, and the color part at the end of the string is all we want to parse out together. So we will say if stir ends with space bags plural, then we are going to remove 5 characters of the suffix. So that's bags and then the space preceding the word bags. If it ends with just bag without an S, then we are going to remove 4 characters. But if it doesn't end with either of those, it's malformed, so we'll just put a check fail here. So now we need to just find where the digits end and the color description begins, and split those up and parse them. So, I mean, we are getting really close to the point where I feel like, yeah. You know what? At this point, actually, maybe I do want to use a regular expression, so I'll say static re2, lazy re2 pattern equals. And what this pattern should look like is we want any number, is we want, 1 or more digits, and we want to capture those. Then space, then truly anything, so dot star till the end of the string, and dot is should match any character, including white space. So basically, we eat up the digits at the beginning, we have a space, then we have the whole rest of the string to the end, and remember, we've taken out, bags or bags here, we've removed those suffixes. Why is it not liking this? Expected colon, semicolon after expression. Oh, it should be else if, not else. There we go. So now we will say, if, well, we should check that we get a full match for the string using our pattern here. And the digit part should go into parsed.count. And the color part, and I'm not you know what, I actually don't think RE2 is going to like trying to put this into a string view, because it doesn't necessarily have the conversion there, so let's just make that a standard string. We can afford the copy, it's fine. So then we will go into parsed.color. So at this point, we should have parsed what we need, and we can just return that parsed thing. So now, for each of these strings that describes something that is contained by the outer bag, like 4 plaid crimson pies, 3 dim plum bags, etc., we so we'll iterate through those, which are now in this rule parts vector. Then we are going to get our parsed bags here. And I'm realizing now that this contained by relation should actually be a multi-map, because there is a possibility of multiple things that can be contained by. Absol flat hash map does not actually have a multi-map equivalent out of the box, so we'll just put vectors in here to represent it. We'll just use a vector and kind of emulate a multi-map that way to have all of the possible contained by relations. But anyway, so the parse bags, parsed equals parse bags. And then what we will do is, so in contained by, the color, the contained by color has as one of its possible containers the container color that we parsed above. And we are not liking this to, oh yeah, well, so we just have to, actually convert that from string view to string. Okay. So that should work. Now we just need to count all of the possible outermost containers, given that we are starting with the particular bag color we want, which is a shiny gold bag. And we want to carry it in at least one other bag. We find all the other outermost bags that can possibly hold it. So this is where we get to the fun graph traversal part. So we need to keep track of all of the outermost kinds of bags that we have visited, because if it's possible, I don't know if there are cycles in this graph or not, but I'm going to assume that it's possible that, like, you could put a brown bag inside a white bag, inside a brown bag, inside a white bag, inside a brown bag, and the outermost bag, of course, could be white or brown. But we don't want to recurse infinitely in that cycle, so we're going to keep track of the outermost bags that we've already been to. I just put in the include for flat hash set there because I didn't auto-complete it. And we're going to initialize that with our first bag. So which is, oh yeah, just the bag color that we already have. Okay, so we're also going to need a queue of, well, I mean, we could also do this in a recursive way, but I'm feeling like doing it in an iterative way because I've been bitten by some Stack Overflow bugs recently. So let's have a queue of all of the outer bags that we still need to process, because we still need to see, what they contain and go so on and so forth. So we'll do standard queue. I don't know why you didn't want to complete that there. We'll include the unprocessed bags. And we will also, I'll just pass this as a string. We'll just, I realize, we could be using string views for a lot of these, but to be honest, the libc++ implementation of standard string, I think, allows you to inline, I think, up to 22 or 23 characters anyway, are just like held right within the representation. So I don't think much is gained by using string view in this case, and we can avoid some conversions, and I'm not going to really get into the weeds of the differences between string and string view here. We'll just use string because it's fine. So this will also start with bag color, and so we'll say that, and why do you not want to initialize that way? We'll just push it back there. Push bag color. So while we still have stuff in the queue to process, so while the queue is not empty, we will look at the candidate bag here, and we'll say, so we'll try and insert it into the outermost bag set, and then we'll check if it's successfully inserted or not, because if it didn't successfully insert, that means that that bag was one that we already visited in outermost bags, and we don't need to process it anymore because it's already been put on the queue, it's maybe already been processed, we want to stop the recursion there. So if we successfully, we'll take the first element from unprocessed bags, the front of the queue, and if we successfully insert it there, then that means that we actually do need to process it more. So we need to put, we need to look up all of the bags that could possibly contain it and put those on the queue of unprocessed bags to continue processing those in the future. So let me look this up. I'm just looking at the is there a version of push for a queue that takes an iterator range? No, there's not. So anyway, we'll go ahead and look up in the contained by for each container in the contained by map for, I'll just to make this easier, and then we'll go ahead, well, we won't. So for each of these possible containing bags, we're going to put those on the queue of unprocessed bags that we need to handle, because it's possible that we haven't visited them yet. And if we have, we'll go back around and, when they do come to the front of the queue, they will already be in outermost bags, so we won't process them again. So then we pop off the queue to remove that front element. And at this point, so what we're doing is we start with just the first bag color on the queue. We we keep on iterating, and then we look at if this is not something that we've seen as a possible outermost bag yet, then we need to process all of the possible bags that could contain it from that map that we made before, that contained by map that we made before. So we add those to the queue. We then finally take it off the queue, and we move on to processing the next item on the queue. Also, this is an iterative version. You could also very easily have written this in a recursive way. Then, to get the answer, we just look at the size of that outermost bags set, and we subtract 1 because we're not counting the one bag that we want to be contained, our shiny gold bag. So, I think that is all we need for our solution to part 1. Except we need actual I/O, of course. So we're going to check that we have 2 arguments. We are going to read all of the lines from the input file. We are going to build one of our bag graphs here. And then for each of those lines, we are going to add it as a rule to the graph. And then we are going to ask the graph how many distinct outermost bags can cover our shiny gold bag. Okay, so now we need to put in all our various dependencies. We need these two containers, we need abscil strings, we need RE2, and we need both of our util libraries. So put our strings in here. Got our hash maps, and then we need we also need the dependency for RE2, where we use regular expressions. I'm glad I have the option to use that. I'm glad I put that in the repository. So first thing I'm going to do is I'm also going to take the example rules in the puzzle, and as we've been doing the last couple of days, just use those as a little test case before we try and run it on the full input. So let's see how it goes. All right, so we've got a problem with part of our parsing with this regex pattern. So well, we see what the pattern is. Let me go ahead and just by way of debugging, let's spit out what the bag string looks like here, so that before that crash happens, we have an idea of what it's actually trying to parse. Okay. No other. Oh, no other. Okay, so that's another possible thing. So that's just a case that we forgot to handle. All right, so we just skip over that because there's nothing. I mean, there's nothing to parse. So let me get rid of that debugging string and see where we get now. Still bad. Okay, you know what? Let's put it right back. Shouldn't have been so hasty. Yeah, and we're back to no other. Okay. You know what? We would have trimmed off the period. I think. Would we have? Oh, man. where would we have? Oh yeah, check. Yeah, so we would have turned off the period. That's why, because we did that at the very beginning. Now let's see. Okay, so it's saying 0. So it parsed everything okay. I think it maybe didn't, but it gave us an incorrect answer, which is 0. We are looking for an answer of 4. So let's try and debug a little bit more. So let's say let's see how this looks, just to make sure that that kind of backwards parsing. So the first line of our the first rule that we have to look at says light red bags contain 1 bright white bag and 2 muted yellow bags. So we should have bright white is contained by light red, and muted yellow is contained by light red. Vibrant plum contains... Yeah, okay. So I think the parsing of the rules is looking correct. So it might be actually the graph traversal where we could be screwing something up. So let's look at that again. So, oh, you know what? Outermost bags should not contain bag color to start. We're short-circuiting right away, because when we try to insert the first one into outermost bags, it's right away saying, oh, we're already done. There's nothing more to do. So we just short-circuited our algorithm early. I'm pretty sure that's going to be it. Okay, out of range. There's always something, man. Always something. So... There's probably an outermost bag that has no container around it, and it's not in the map, and that's why contained by isn't working here. So let's go ahead and make this let's make this safe for cases where the current bag that we're looking for is not in that contained by map, because nothing contains it. It's an outermost bag unto itself. So we'll do contained by find. We'll use the find method to find the current bag. And if that iterator is at if that iterator is not past the end of the container, that's when we actually want to go and add all the additional stuff to process here. So, I mean, this would actually just work as is, but I don't want to incur another lookup into the map, so we'll just say in that actual container from the iterator. Let's see where we are now. Okay, we have 4, which is what the puzzle text says is the correct solution for the example. So let's try it on our actual input and see how many outermost bags you could possibly have. 302 different color options. We are just lousy with luggage right here. Let's see if that's correct. 302. All right. Had to do a little bit of debugging, the moral equivalent of printf debugging, but we got there. It's getting pretty expensive to fly these days, not because of ticket prices, but because of the ridiculous number of bags. Okay. Consider, again, your shy gold bag and the rules from the example. How many individual bags are required inside your single shiny gold bag? Okay, I have to imagine that this graph actually doesn't have cycles now, because if the graph did have cycles, the answer would be infinity. You would have to have a shiny gold bag, a gold bag contain a brown bag, contain a gold bag, contain a brown bag, you would have an infinite number of bags. So I'm reasonably sure they gave us something without cycles in the graph right now. But to do part 2, let's just copy our solution because we're going to use it as the basis here, and we're going to run things in the other direction. So we're, instead of having contained by, we're going to have a contains relationship. So puzzles day 7 part 1.cc, we're going to copy that just to start part 2.cc. Okay. So and we'll go ahead and refresh this. So now we are going to build up a graph. Instead of a contained by relationship, we're going to have a contains relationship. And so we're just doing it backwards, but it's also important that we have the count here because we need to count up the total bags that we're visiting. So instead of just a vector of strings of names, we're going to have a vector of our parsed bags struct because we need to have those counts. So yeah. So now contains is going to start with So we're just going to save a reference to the vector of contained bags inside the container here so that we're not looking up into the map multiple times with each iteration of this loop, just as a little optimization. So then contained dot yeah, we can just push it right back actually. Oh, but okay. We need to use a different variable name here. Okay, so now we've built the graph going the other direction, showing the contains relationship. We can get rid of this count outermost bags here because we don't need it for part 2. Although we might actually want to use this as the scaffolding for the algorithm because it's going to be something pretty similar to what we did previously. So I don't think we need that set. Yeah, okay. You know what? This time, just for the heck of it, to show a different technique, I'm actually going to use a recursive solution here. And hope that I don't run out of stack space. So, we start with 1. So to count the held bags for a given bag, we first look up that bag in the contains. So in the contains map, so we find an iterator contains.find bag color. In this case now, I've flip-flopped back and I want to use string view with heterogeneous lookup. Now, if the iterator is at the end of there, it means that that bag doesn't contain anything else. So in that case, we just return 1 because this count held bags is going to be inclusive of the bag itself. If we do find that it contains stuff, so we're going to say int total bags equals 1, starting with this bag itself, and then for each of the parsed bags that it contains, we're going to look for its number of held bags and then multiply that by the count of that color of bags that it contains. So for each of these, the total bags, we are going to increment by the count of the bags that it's holding times the sum total of bags that bag actually represents with everything that it holds. So that's going to be a recursive call to count held bags with that color. And then we will return the total bags. So I think that's our solution now. We just need to change that to count held bags for shiny gold. Let's go ahead and make the build target for this. We should have all the same dependencies, although I don't actually think we need the set anymore. I don't know if I actually removed that from the source code yet, but I will, because we don't need to keep track of what we visited yet. And I actually don't think, now that I know that there are no cycles in the graph, I know that we didn't need to keep track of that in the first place either, but I wasn't sure in part 1. Let's go ahead and run this on the test input and see what it tells us. It says 33. Okay, so that's not correct. We messed something up here. Because the it says here's another 32 bags. We're off by 1. So it's the total number that's contained. So we'll subtract the 1 for the outermost one, and then that will give us the correct result. And so we have another example that they gave us. We'll go ahead and call that test 2 and just run that also, as a double check. And that is giving us 126 is the answer, which the website says is correct. So now let's try it on our actual input and see what we get. 4,165 bags. We have a lot of luggage to buy, folks. But let's go ahead and see if that's correct. We got it! All right. We were slowed down a little bit by kind of some bugs that we had to fix for ourselves and read the problems a little more carefully. Let's see where we go. Okay, about par for the course for us so far. So talking about today's solutions, there's two different, I'd say that there are two challenges kind of that this represents. One is something that we've seen a lot on previous days, which is just parsing text input and kind of, munging that into the actual data structures in the program that we want to work with. And here we have kind of a mini language describing how bags contain other bags. And parsing it is not really trivial. So, we have kind of a lot of messy string manipulation. I used regular expressions for part of it. I probably could have used regular expressions for it a lot more if I were better with regular expressions. And there were parts of the language that I was initially ignoring that I had kind of not fully read in the program description, like the no other bags that we had to deal with. So part of it is just a text processing challenge. The other part of it, which I think is the more fun part of today's puzzle, was the graph traversal, the graph algorithm. So what was cool about this is, we could build this relationship of bags containing other bags one way or the other. We could build it as a contained by relationship, which is what we needed in the first one, because we needed to find all the different outermost bags that could ultimately contain our shiny gold bag. And then in part 2, we had the edges of the graph going the other way, and we had to find all of the bags that were transitively contained by our shiny gold bag and count them up. In this first part, especially when you're doing a search through a graph, it is something that lends itself naturally to recursion, but you can also just write it as an iterative way. And there are a lot of algorithms in programming that have both an iterative and a recursive version. And I think a lot of times, to my brain at least, and everybody's different for this, but to me, I often think the recursive version of a solution seems a little more intuitive and a little more natural to me, because all I'm saying is that, at the top level, and we did a recursive solution in part 2, you can see that we are not really worrying about the details of everything to come, everything that could be under this. Our call stack could get really deep with all the different ways that bags can contain each other. But in this function, it's pretty simple. We're just saying, we're counting on recursion to solve that problem for us. We'll figure out everything that's down that whole chain of bags within bags within bags. But we'll eventually get the answer here and just add it into our total. And to me, that is a kind of simple way of looking at the problem. In part 1, we could have done a recursive solution for that too. In part 1, I chose to do an iterative solution, which basically just said, instead of recursive calls where this function calls itself, and so basically the way that a recursive solution for part 1 would have worked is for each possible containing bag, we would have then recursively called and found all of the containing bags for that, and so on and so forth. We really, we still... in this one, I just chose to say, okay, we're going to have a queue of all the things that could possibly contain this bag, all the outer bags that we still maybe need to process, and we'll just keep on processing that queue until we totally drain it, and then there's nothing more to add, and we've gotten to the end of the solution. Logically, these are equivalent to each other in terms of a practical programming kind of thing. If you do a recursive version of if you do a recursive algorithm, sometimes, depending on if it's tail recursive or not, the compiler can kind of optimize it away and maybe even change it into an iterative solution. But as a general rule, you might, recurse very deeply on the stack, and you use more and more memory the deeper in the stack you get. And in a single-threaded program like this, you will have plenty of stack space, but I have run into problems, especially in like a real-life production environment in a server, where you don't have, near unlimited stack space. You actually have a fixed size stack because each thread needs to have a different fixed size stack when it's created, and if you run out of that, you're probably going to hit some kind of a memory error, like a segmentation fault. So if you think that you might go really deep in a recursive algorithm, you better change it to iterative if you want to avoid problems in that scenario. But for Advent of Code, for toy problems like this, for puzzles that we're trying to solve, that's not as much of a concern. And I should also add that that kind of stack overflow issue is not necessarily a concern for every different kind of programming environment. It's definitely the case when you're using C or C++, something using pthreads or something similar like that. But for instance, the Go programming language, its memory model is a little bit different, such that if you it has pretty decent escape analysis in the compiler, but basically, if you take the address of something, if you take a pointer to it, then that thing is automatically going to get allocated on the heap and not the stack. So pointers will stay valid to it no matter where they go. And so what Go does is it actually, if you're about to run out of stack space with a call, it'll make you a bigger stack and then copy all your stack over to it and keep executing. And because of that guarantee from the memory model that anything that you retained a pointer to was on the heap and not the stack, it doesn't move around in memory, and that works. So like Go actually starts with much smaller stacks than C++ tends to, and you really get into, and I think it starts with 8K stacks by default, whereas in C++, it really depends on your environment and how you configure it, but I think 64K is more common. But yeah, in Go, you don't really have to worry about this problem, unless, of course, you recurse infinitely. Then you're still going to run into problems, but the stack can sort of just grow naturally. But the C++ memory model doesn't really allow you to use something like that. So with that diversion, talking about the difference between the iterative and the recursive solutions, I think in a puzzle like this, they're both equally valid, and I think recursive is a little simpler. Having this set of outermost bags, we might still have needed this just because, I don't know, would there have been multiple? The graph is definitely acyclic. I don't know if it's strictly a tree, because there might have been multiple ways to get to certain outermost bags, so having this set might still have been necessary. I don't know. But yeah, we're getting into some graph problems. That's always fun, and I'm excited to continue working through these problems with you, continue as they get a little more complicated, a little more tricky. Hopefully they get more complicated in fun ways where we have to, like think about how we're traversing a graph, as opposed to more complicated in terms of really tough string processing to do. But that has been my experience in past years. So thank you, everybody, for joining us tonight. I'm about to wrap up the stream. Remember, you can always catch the replays of these streams for every day on my YouTube channel. That's youtube.com/spoonboy42. You can also see all the code for my solutions. It goes up on GitHub. My GitHub is at, this particular repository, I'm going to put it up on the screen. It's github.com/Craig-Chasseur/AOC2020. You can look at all the code there. Thank you again for joining me once again tonight. I look forward to seeing you again tomorrow and throughout the month as we solve more of these puzzles. Bye-bye, everybody.